So so let's continue. That's why actually. So what I observed, what we showed was basically just to summarize. So RS coding is kind of MDS codes are used. That's the way they start with initially, and then with the local things we have a regenerative code, one flavor, and LRC code, local reconstruction code, are the two flavor that has come out of the need from the both from practice, and this is hidden to a more theoretical circle and brought out the issues of coding in the storage domain. So obviously there was also another community that was working called from RAID, redundant array of disease, and sometimes it has some part of the MDS property, and it could be used for even smaller devices and stuff. So if you look at the type of papers, you see you get a large number of papers with regenerative codes, LRCs. These two are distinct areas of things working now. There is another class of codes which are called PMDs codes, and I actually circulated that to you people, and that is the one. This actually construction of partial MDS. So wherever you see, even with LRCs, what you see, because of the requirement that the nodes need to be local, that has some penalty in terms of the minimum distance, and so you lose the properties of MDS a little bit, right? But with this one paper, so obviously, but let's try to understand really what they are trying to do. So the idea is that here you go with you code with let us say some R rows here, N rows here, R rows here. It's a vector code. R rows here, N nodes here. Out of that N nodes here, there are M code column. There are the parity columns M. So M is that. So obviously it has so each row is a MDS code. Okay, each row is MDS code, and subsequently, let us say all these are MDS code, and there will be some few other small number of global parity that works on the whole thing, and whole thing itself is a kind of an MDS code. Whole thing is an MDS code as well. So that means if you refer this is an MDS code but every row is also MDS code. Now, so because it is an MDS code, it can always tolerate M column failures. So if there is any there are some errors happening in anywhere in the M columns, anywhere M columns it can tolerate, right? So this is the idea, and PM code for any R with S is equal to 1 were known already, but this is a very recent paper on actually constructing a code with this property. Okay. So so obviously you can see that these are all erasure codes, and there was also another type of codes were used mainly when people were designing small memories. So they have a what you call sector. So depending on how the memory is designed, the errors happen in a particular sectors, and so you can correct them. For example, there will be so maybe first to understand the issues here, if you can actually understand the 5 failure scenarios explained here, that will actually, and you will understand. Let's not worry much about the sector code. Sector code actually think that it can only detect, for example, it doesn't differentiate between error happening in one bit or the whole column. Okay, sector. But leave aside sector. Let's try to understand first PMDs. So here is this pattern. See, for example, here there is 1, 2, 3, 4, but each line is an MDS code. So obviously it's M equal to 1 here, so it can recover from it's trivial. right? It can occur. So you can construct a generic construction, you can do for such thing, but generic construction may not take other complicated things. So we will assure that what is some unique novelty in this code. So that is this, and here there is this another PMDs code here. So for example, here there are many errors, 1, 2, 3, 4, 5. That means 5 nodes are done. But since all the errors are in all the failures are actually aligned to the first node, and you can easily correct that one, right? So you basically so what you do? So how do you? So if you just have a MDS property, can you correct all the pattern here? That's the next question. Just MDS property you couldn't, right? So because this one has only this row has only one error correcting, but it has 2 errors now. This also has 2. So how does this code corrects that? So that you have to go through. So for example, these 2 ones it can correct. Once you have these 2 ones, look, it has a global s equal to 2, right? S equal to 2, so it can correct 2 global errors and all 1 error. So first the code has can do this simultaneously. It can take 1 column error, okay, which is erasure, and the 2 global errors. So these 2 it can simultaneously take it, because that's the case, and this one can be used to decode this, and the same is here. So this one is this will be connected with the MDS property of m equal to 1, and these 2 are additional 1. So whereas in this case also the same thing. So whereas see for this one here, even the sector disk thing also he says it can be done, because it can do all of them. So there is 1 error here, 1, 1, 1, this can be done. Then after that, so this error it can correct, and then these 2 will be corrected. Whereas but this is a special one, it can only a PMDs can correct. That's because these 2 he corrects by single error. Then after that, so once the rows with only 1 erasures are corrected, we left with 2 rows with 2 erasures each, and none of them is in the same column. So this is the challenge, is to construct PMDs and ST code for general parameters. So in this paper we address this one for, he will go for s equal to 2. So for any m s equal to 2 he corrects. Each one is actually a 2 MDS code, 5 plus 4 plus 2, so it can correct. So 5 plus 4 information bit, so it can s equal to 2. So 5 1 parity, so it can correct any 1 row errors. So let's come back to, actually I'll mention something about the coding idea here, and then probably that might help you to look at the issues. So you can see that even though we have n by RL, you can't use separately. This the whole code. This is basically a code that takes care of every column here. For example, this is a GF2, it's actually a code of length r power n, where some portion is deliberately chosen as 0. So, but and this particular one, the H1 to HR, this one takes care of the global parity check matrix. So this code actually can that way to handle. Do you get the point? No. So for example, here when I put here, the code is, this code here and code here are not different. So if you have a general MDS code, the information you derive from one row I can't apply in other one, whereas here the construction actually takes alpha belongs to GF2 power W with Rn less than alpha. Then we will go through this parity check equation. Now in order to make sure that that's a parity check equation, that is where he does all the finite field instructions. So he is going to show that the determinant of that matrix is non-zero, and hence you can do it. So for example, he does with 2 rows here, that is the last 2, that is why you get S equal to 2. Can you come up with any 3 rows? Okay, then it becomes R S equal to 3 code, it will be completely a new work. Okay. So I think what we studied in this course, this H0, these ones or H1 individually are Reed-Solomon code, it can correct something we have studied. Now you put together in a bigger matrix, and so now it become a global code much of length R power n. Then you look at whether it is a parity check matrix and all, that becomes quite complicated. That is what the things done there. Now unlike other things what we did, we in our presentation we also said both the generator matrix and parity check matrix. So you could use both. So the paper follows, because that is what I remember, he only does with parity check matrix. So because we want to do for S equal to 3, so you have to think separately, and he chooses a particular field size. I mean, so for example, in his case this one is the field size is not very large. So maybe if S is equal to 3, if you get a general solution, then field case may be different. So you have to think in many different directions. So this is a kind of quite open area to do now. So if you have a solution for general S, and again number of errors that it can, the definition number of errors that it can correct is because as you correct towards like this, it is sufficient that the sigma Si is up to that point, when you add the number of errors up to that point should be within the capability one. So you could still download. So that is why he gets an advantage compared to the sector disk code. Sector disk code, they simply takes the columns into the things, because they can correct all columns together. So that's the kind of definition he does there. So if you understand this definition, you will probably start moving to a next direction. So this is the kind of definition. So you have so you say C is an MS partial MD code if for any S1, S2 to ST. So you can start build up the errors happening from top row to bottom row, S1, S2. So for example, S1 could be an error. So each Sij is greater than or equal to 1. So any row you can have more than 1. But sigma of all up to j is yes, and for any I1, I2, It such that they are within R1, it can correct up to Sj plus M erasure. So it can correct together but Sj plus M erasures. So that is why that actually explains to you why in the complicated only the PMDs can do. Whereas in ST the difference is that if these locations of course are to be less than n minus 1, the sum as greater than 1, and there is no this particular condition, that is Sj greater than 1 and up to j it is yes. That is not there. You can actually go up to sigma, everything is up to t is yes, can correct up to these errors provided all the errors are in the same they are in the same row, have been erased, in the locations have been erased. So if some extra conditions is needed for the sector disk, the PMDs takes care of that one, and he does it with GF2 power W, which is much smaller field, and it's all binary field. And you can see that the determinant calculations when he shows in the further paper, he uses the determinant of 1, and because in case of a binary field 1 the determinant of 1 is 1, so it's so determine in the sense that the non-zero, the inverse of 1 is 1, so it becomes simpler. So it's basically a kind of a linear algebra working on a particular structure of a generator matrix and trying to compute the the determinant of that matrix. As soon as he gets a non-zero, then he gets a solution, and this actually can compete with other RAID technologies and can be implemented for both code like systems like Hadoop or cloud storage, as well as the simple devices like memories goes into smaller things. So whether in the where you put in the hierarchy of memory, this can work. So that's why this is a kind of a joint effort from Microsoft and IBM. I think these people have said, and this is another one. So this is so I think if you read further, maybe we could discuss a bit more tomorrow on this, unless you have some other questions. One of the things is basically, so as I told you, since now R equal to S, so this is at the moment, so he choose S is equal to 2 is solved. If you want for general S, that's still open, okay, and he choose the size to be some order of alpha. So for example, here alpha is the number of rows, alpha power L equal to 1. So okay, so this is the he will choose the minimum value of this. So alpha is a primitive element in GF2 power W. So you can say this has some capabilities equivalent to this. So it is Rn and n minus m, and he goes with this particular method. Okay, so you can see the structure of the code. That code is very simple, and so this code is is just as you can see, it's a power of alpha is the same thing that we discussed. Okay, so this is the global part, and this is the part. So in fact, this can actually takes 2 erasures, 2 column erasures, and 2 global erasures. So this code H2, H1 is the one which is like how much is that? It's for 4 5. This is the code. So these 2 equations, you remember this actually work on the entire code word, the whole you open up this matrix into a bigger code word, and that's the code word is used here. And because of each one is a kind of each block is also a kind of RS code, because it's like a RS code, you can recover up to that much sigma SI term errors. So SIs could happen in, so this is the SI happening in first error, second block, third block, and so forth. So second row, third row, and fourth row. So the code has been expanded. You think, so then you can probably go and understand. You can see that all is 0, right? So this is, so you can see that this comes 0, 0 here. This is the last bit. So that means, okay, one way to see is that, like say here you can see you have a 4 information bit. The last part is simply the XOR of the previous one, and that tells you here. So this is for the first row. When you add it, that portion is 0. All first rows. Okay, so maybe I can explain this using a simple diagram here. So I'll now write back into the code in as an array. Okay, this is how much you need. Basically, five. Okay. So this symbol is obtained as the checksum of all of these. This symbol is obtained as a checksum of all of this. This is a checksum of all of this. This is a checksum of all of this. This is a checksum of all of this. Further, these 2 checksums about the entire thing is added here. So how to place that is that what you have to see from the things. So you can see that when this h means you can multiply. So the length is how much? R equal to 3, right? Now it makes sense. So there is only 3 rows there. So together, so you basically you have 5 into 3 15 length code, and this is actually he chooses it for alpha 14 equal to he demonstrates in g of 2 power 4, I think. So this is the simplest example, but it's all, you know, once you get a solution in such a small field, you could also get a solution in a little bit higher field. So what you have to ensure is in the parity check matrix you have enough non-singularity, because that's what the, you know, the bounds we mentioned in the Adrish lecture, that comes into picture here, and I had to show that the determinant is 1, because that means those many columns are 1, and you get, so it can take now any 3 columns, any 3 errors happening, any 1 column and any 2 errors it can correct. So we still have time, so could probably do the Sorbas one, and so so yeah, I think so. So what we do is that we'll look at the same thing maybe we saw yesterday, MXR and RS code decoding.